Okay, this is our gas laws foldable that we made in class. We took 5 sheets of paper and staggered them, showing one blue line for each one. So that gives us 10 tabs altogether. We titled it Gas Laws, then our kinetic molecular theory. We got it from here. One of your homework assignments was to add all 5 of the kinetic molecular theory postulates under this tab. Then we have Dalton's law, Boyle's law, Charles's law, Avogadro's, and Gay-Lussac's. We're going to hit combined and ideal after the break. So let's go ahead and get started with Dalton's law of partial pressure. Dalton's law, our formula, is the total pressure equals the sum of the parts, P1 plus P2 plus P3. Okay, I did have a little goof on this one. I want the definitions at the top. And I want the questions at the right here. So this one's backwards. So take this information and put it up here. You can see I did that for Boyle's law up here. So I'm sorry about that little goof up. If that blows your mind too much, just go ahead and do it like I did it. But stop the video. Fill in this information on your foldable, and then let's get started on Dalton's law. Okay, Dalton's law includes pressures of multiple gases. When I blew into the balloon, you saw, or you didn't see, I'm sorry, you saw the balloon expand, but there's the pressure from the nitrogen and the water vapor and the oxygen and the carbon dioxide, and everything I blew out, I exhaled into that balloon, made up the total pressure going on the balloon. So it includes pressures of multiple gases. The pressure units need to be consistent or the same. Remember, our pressure units are millimeters of mercury, atmospheres, kilopascals, and psi. Of course, there's newtons and torr and many, many other ones, but we only are concerned about those first 4. And then here's our formula. Okay, so let's work a problem. I have 2 foldables. This is the one I use in class, and of course it already has the problems worked out. So I'm going to, the second one, I made just for this video. So you'll see me switching them out quite often. Okay, so Dalton's law of partial pressure. The way we're going to work a problem every time is we're going to label and circle. So what is the total pressure? Let me get a different color pen here. What is the total pressure? So this will be my P total. In a container, if gas A exerts a pressure of 742 atmospheres, there's my P1. Gas B exerts a pressure of 1586 atmosphere, there's my P2. And gas C exerts a pressure of 550 atmospheres, there's my P3. Okay, so we always label it. On one side, we're going to write our formula. P total equals P1 plus P2 plus P3, because I have 3 partial pressures. I circle my unknown and I get my unknown by itself. It's already by itself. So we're going to draw a little squiggly line. I want formulas on one side. I want the math work done on the other side. So I'm going to write the equals. So we have 742 atmospheres plus 1586 atmospheres plus 550 atmospheres. So we substituted that information in. Let me zoom in a little bit closer so you can see better. And then we're going to add. So you're going to add these 3 together, and that gives us our partial pressure of 2,878 atmospheres, or 2.88 times 10 to the 3rd atmospheres. Actually, I guess that should have been just 2 sig figs, but that's okay. All right, so that's Dalton's law of partial pressure. The next law we're going to look at is Boyle's law. Ooh, can you see it? Boyle's law, very painful. Okay, so Boyle's law is going to relate 2 different volumes and pressures. There's an inverse relationship. An inverse relationship is a relationship where one goes up, the other goes down. And we can see that in this graph that you have to be able to recognize. So So here I have a little manipulative for us to use, and it's PTV. In Boyle's law, temperature remains the same. So when volume increases, we can see pressure decreases. Or when volume decreases, we can see that the pressure will increase. So this is a good little manipulative to have that you'll be able to use. Okay. Now the next thing I need us to learn how to do is move our decimal 3 places to change from milliliters, 45 milliliters, to liters. Okay, so that's something that's real important for us to do. So let's go over to our sample problem that you're going to work. So I have Boyle's law here. Okay, a 45 milliliter sample. This is my volume 1, and I want to put it in liters. Again, like I was showing on that other problem, 45 milliliters will be divided by 1,000, which is the same as moving my decimal 3 times, so 0.045 liters to change. Okay, and we're going to always change to liters because our problem, once we get to the ideal gas law, our answer will be incorrect if we're not in liters. Collected under a pressure of 190 kilopascals. That's my pressure 1. What will the volume be if the pressure increases to 260 kilopascals? That's my P2. Oh, I'm sorry, and this is my V2. So let's go ahead and write our formula. V1 P1 equals V2 P2. Our unknown is V2. We're going to circle it. We get it by itself. We put V2 here equals. Anything the unknown multiplies with becomes a denominator. The rest is our numerator. Okay? So then we're going to fill it in. Our initial volume is 45 milliliters. We said we need to move that decimal 3 times, so it'll be 0.045 liters times 190 kilopascals divided by our pressure 2 of 260 kilopascals. Okay. We do our math and we should get 0.033 liters or 33 milliliters. If you want to write it in scientific notation, times 10 to the minus second liters, or 3.3 times 10 to the first milliliters. Okay, so let's see if our answer is correct. Our pressure increased, so therefore our volume should decrease. And we went from 45 0.045 liters to 0.033 liters. So that looks like it worked. If I'm going too fast, pause the video, rewind, whatever you need to do. Okay, so our next law is Charles's law. And Charles's law relates 2 different volumes and temperatures. The temperatures must be in Kelvin, and this is a direct relationship. Make sure you can recognize this direct relationship graph. As one goes up, the other goes up. Okay, and our formula is V1 divided by T1 equals V2 divided by T2. Okay, so our conversion to go from degrees Celsius to Kelvin is add 273. Good. Okay, so let's work a problem. Flip up, and we're under the Charles Law tab. An 85 milliliter sample, and so this is my V1 that needs to be in liters, of a gas was collected at 14 degrees Celsius. This is my T1 that needs to be in Kelvin. What will the new temperature be? So there's my T2 in Kelvin if the volume is decreased to 35 milliliters. So there's my V2. Okay, so our formula is going to be V1 over T1 equals V2 over T2. The way we can remember this is we watch Charlie Brown on TV. Temperature is always at the bottom. Okay, so we're going to circle our unknown, which is T2. So T2 equals, so we're going to get T2 by the on the bottom. T2 by itself. Anything I multiply with becomes the denominator. So V1, because remember this equal sign means I can cross multiply that proportion. Okay, so that equal sign means I can cross multiply. So that would be V1. What's left is V2, T1. Okay, so now let's plug it in. I'm teaching you all how to guess. We're underlining and circling our given and our unknown. We write our equation, then we substitute it, and we will solve it. So we're learning to guess properly. Our V2 is 35 milliliters, so it'll be 0.035 liters times 14 degrees Celsius, but I have to add 273 to it, and I have to divide it by V1, which is 0.0, I'm so sorry. That's why I always write in pencil, right? 0.085 liters. And we do the math, and we get, our liters will cancel, and we're going to get 118.18 Kelvin. Oops, because this is Kelvin. And so there's our final answer. We don't put Kelvin in scientific notation. All right, Avogadro's law. Avogadro's law relates two different volumes and the number of moles, because Avogadro is 6.02 times 10 to the 23rd. That's his number, which is moles. All right, there's a direct relationship, and this is our formula. The initial volume divided by the initial number of moles equals the final volume divided by the final number of moles, and our graph. Okay. All right, so let's work our problem. Again, I'm just on the same flap. So 2.5 moles, that's our N1, of a gas occupies a volume of 1.2 liters. There's my V1. What will the volume be if the total number of moles increases to 3.7? So there's my N2. Here's my V2, that is my unknown, at a constant temperature and pressure. So let's write our formula. Remember, Avogadro sounds like avocado. They're very nutritious. So we're going to V1 over N1 equals V2 over N2. Avocados are very nutritious. We're looking for V2. We circle it, put it by itself. Anything the unknown would multiply with becomes my denominator. The rest is my numerator. Whoops. Okay, so anything my unknown will multiply with becomes my denominator. Now we're just going to substitute the information in. We have V1 is 1.2 liters. No need to change that. Times 3.7, my N2 moles, divided by my initial number of moles, 2.5 moles. My moles will cancel. I'm left with liters. And I do the math, and I get 1.78, liters. I was about to write moles, wasn't I? 1.78 liters. Okay, so I'm almost out of time for this video, so I'll have to hit Gay Lussac on the next one.